So I guess we can start, but before I can you hear me? So before I start, I would like to draw your attention to the homework 3 has been posted on the web yesterday. You have like 10 more days, more than 10 days to get it done. I think it's 12 days. So it's basically go over the random variable. So if you know how to handle the examples in the class, then you shouldn't have any issue with this one. And since the TA has grade homework 1, and some of you asked me the solution, so the solution. So let me know if you find any typo in the solution. I guess that's pretty much. So the goal of today is trying to finish this topic, sampling distribution. If we're not, then we cover almost all of it, and then we go to estimation. So as we said last class, this is a starting point of second half of our course, which is trying to say is we use the data to have some analysis, right? And after this one, we will do estimation, and then we'll do hypothesis testing and over and regression. So we need to, this chapter, this topic is a bridge of the probability and statistics, right? And the first thing we learn is, I think last class we covered, is a simple random sample. It's being simple in the sense that every element in the population will be chosen with equal probability. And the choice of the sample is independent in the sense that choosing one element doesn't tell me whether the other element is being chosen. Okay, so this is a simple random sample. It seems very simple, very easy. That's why simple random sample. But this is very hard to implement in practice in various sense, right? As I mentioned, if you're online survey, basically you miss the people who don't serve online frequently, right? Those like seniors or those who don't use, who have no connection to the internet. And if you do offline survey, on-site survey, the thing is that you have to pick certain particular locations, and it's difficult to pick those locations at random, right? It's very likely, say, look at our campus, right? How to have a uniform location, right? I mean, you have to figure the location where average people would be there, right? If you go to somewhere, some location, then you miss some of the people, right? Suppose you have a do a survey at the subway station or the MRT station, all right, the train station, and basically you miss the people who take the bus to school, or who drive to school, or who walk to school. So that's the main idea. And one important property of the simple random sample is every observation will have the same mean and variance as we would see in the population. So that is the main idea connecting the topic 1, topic 3, right? Let me, it's good to emphasize again. So what we have is we have a population we're going to study, right? Say in this society or in this village with many people, right? Suppose there's a population we're interested, right? And suppose we have infinite amount of money, right? Then we know everyone's income, and then in that way we can have a say a histogram or a bar chart, right? Income, okay, and then we can have plot something like this, right? Okay, or income or number of packs, right? So your number of packs will be discrete, right? Income will be continuous, but either you can put a plot graph or a histogram, right, to represent this data, right? And also you can calculate the mean, which is the mu, and variance. Okay. Do note that this variance will be over n, okay, not over n-1, because this is the population, right? If you have everything there, put the mu here. Okay, so this is the data which there's no probability. Okay, everything you collect from all observation, and this is what we have, right? This is the topic one's idea. Okay, topic one's idea. So this topic one's idea. Right, summary statistics, that's what we learn. And the next thing we know from probability theory or random variable is we are not going to study everything, right? So suppose the thing is like we just randomly pick up one guy, okay? Okay? Let's denote this as observer Mr. I as XI is XI's income, okay? And before you draw that, right, because randomly pick, right, a simple random sample, pick this one randomly, right? And this guy, okay, what would be the random variable looks like, right? Actually, we can use the P and the F to describe it. Suppose I use P, maybe number of packs, right? And the P looks like what? And this guy actually looks like exactly this, but this is P, okay? This is the probability function, right? Or if this is income, then it will be similar. You have a F, right? Just the same shape. The same shape will follow what happened, right, in the population. In particular, if you look at the expectation of XI, okay, is exactly mu, and the variance of XI is exactly sigma square. Okay, so before you draw the sample, okay, there's a random variable depending on what you draw, and the mean of this random variable is mu, and the variance is same. Okay, so that is what we learn when we have a random sample. Okay? And if you draw another one with the same idea, right, we'll follow the same. XJ will follow the same pattern. Each random sample will have the same mean, mu, and variance is sigma square. And if you have compared the 2, 1 and the covariance, because simple random sample, the covariance between them is 0, right? So it means that they're independent. Okay, so that would be the meaning of simple random sample. And as an illustration, I think we we talk about an example, right? The sample is we look at the sample mean, right? Because here we have go back to here is we have a bunch of observation, right? And very often we are not interested in individual observation, right? And the main thing actually in our course, mainly focus on try to learn mu. Okay, the mu is the thing that we are most interested in, because say we want to learn the average income of the society, right? There's something we want to know, right? Of course, sometimes we also care about sigma square, but our main focus is still the mu, right? And of course, probably you would want to know the median of the society, may be another thing, but that would be something beyond our class. So we just focus on mainly to estimate mu and sigma square. Of course, we also want to ask kurtosis and skewness, but the main focus of our course is try to understand the average income and the variance of the income, right? Or the mean of the number of packs or the variance number of packs. So that is the main idea. So immediately out of your head, actually you would think to estimate mu, okay, or to find mu, one of the good ways is try to look at something like the sample, right? Because look at this is the expectation of each observation is accurate mu, right? So you would expect that the average of these samples would also have a closer to mu, right? So so that's why the first thing we care is the average of this observation, right? Or average of this observation, okay? And do note that for each observation xi is a random variable, right? So some average of the random variable is still a random variable, okay? It depends on what it is, okay? And I think the first thing we try to prove for the last time we just end is trying to prove this the expectation of the sample mean exactly mu, okay? The proof is very simple, so I think it we can go to the proof because this one is very simple. Just let you see the proof, okay? The idea is the following: x bar is x1 plus x2 up to xn divided by n, okay? So the simplest thing you can think is x bar is x1 plus x2. Agree, right? And actually the proof in the note, but I just write down in this way. So this is the second step, okay? The first step is trying to see the following, okay? We have already said by simple random sample, this is just mu, right? Same as this, right? And same as the rest, right? Okay. So then the next step will be expected n x bar, right? Is expected x1, right? That is what we have, right? Just putting this inside, right? And we learn expectation, the sum of expectation, right? You have that in your handout, so you don't have to write that down, but I just trying to this everyone just mu, right? And this remember what we have is you multiply by constant, you just take it out, right? So that n mu on the right hand side, okay, the n cancel out, so you have this, right? So that proof, I mean, of course, you don't need to worry about the proof, but this is try to show you that the expectation of sample mean is just mu, right? Because the answer is very simple because each guy is mu, right? Each is mu, right? So sum of them is n mu divided by n, it's just mu by itself. Okay. Of course, this is just very trivial proof. I mean, this is on the slide, but I think it's so simple. Just try to show you this is the case. Of course, we are trying to show you, and by example, very soon. But this is a very important property of sample mean. Is what it said is if you suppose hypothetically we do the sample many times, and average of those all the sample mean will exactly what we want to get, the population mean, okay? But do note that this is hypothetical. We just do one sample anyway, right? But suppose we do many times, then we'll get what we want, right? And And that is very important property. Actually, later, the next topic, or this week or next week, we'll learn what we call unbiasedness. Is on average, what we're trying to do will hit the target. Okay, but that we will left this for the next topic. But that is the main thing. But try to convince you this is the right thing. Graphical is like this, right? If you have many sample, each sample is sample mean, and your average of this sample mean, okay, is called expectation of the sample mean, and actually this equal to mu, okay. And let's convince you why this is correct, okay. And consider we have the population consists of three number 1, 2, 3, right? And you may imagine this is maybe the income of a guy, right? Income of a woman, or income of a senior guy, right, or woman, right? And their free income. And suppose we have all the information, right? We know this. The population mean will be just 2, right? Because 1 + 2 + 3 over 3, right? Now let's consider the case of sample size of 1, okay? Just take one subjects from this one sample from this population, right? And in this case, right, and it will be sample mean, okay, will be either 1 or 2 or 3, okay, because only 1, right? Sample means itself, and equally likely, okay. So the expected sample mean will be 1 will probably 1/3, 2 will probably 1/3, 3 probably 1/3, okay. So at the end of 2, so this is the same, okay. Here I demonstrate one thing is, if I have sample of 3, so population has 3 elements, and we just do simple random sample of sample size of 1, and the expectation of the sample means exactly the population mean, okay, which is this is mu, right? So we just demonstrate this, same as this guy, okay. So the next thing we want to show is actually we end this in the last class, right? This is if suppose you have 2, right? Remember, a guy has $1, the woman has $2, and an old man has $3, okay. So if you do simple random sample, it depends on whom you drawn, okay. Remember, each draw is independent, okay. So the first draw you draw the guy, you can still have a guy again, okay. So that's why if you have guy, okay, the same guy, you have 1 and 1, so the average income is still 1, right? Here, if you're a guy and the woman, the sample mean will be 1/2, because 1 and 2 is 1/2, right? Same idea here. If you have a guy and the old man, then will be 2, okay. So and so forth. We fill up this 9 entry, because it's 3 times 3, right? And each outcome is equally likely, right? So you have 1, you have 1 of them, right? 1.5, 2 of them, and you have 3 of 2, 2 of 2.5, and 1, 9, okay. And you can calculate this expected value, right? You just multiply and plus, right? The same idea, okay. We get 2. So this demonstrate you have 2, okay. Is the same as the population mean, okay. So if you have nothing to do, you can try sample size of 3, okay. It's a little bit more complicated because you have 27 outcome, right? And but you will see actually they were the same, okay. There will 23 outcome if you have sample size of 3, but I'm not going to list it, and you still have the same answer, okay. So this is the first thing we know, okay. Is that okay? So the average of the sample mean or expectation of sample mean is actually the population mean, Okay. Now, if this is okay, then we go to the next step. Okay. The next step is we know the expectation of sample mean. The next thing is we want to know the variance of sample mean. Okay. This variance sample mean, the proof is again very simple. Let me prove it because I think that is worth the proof. Because don't worry, I just proved this too in this class. I'm not going to prove anything more. Just let you see, but because I think that is important to see why we learn this kind of a lot of variance formula is important. Why we learn. Okay, the proof is very simple. X bar, just write x1 up to xn. It's already in your slide, so just write down to show you how the step being done. Okay. The next part is because n over 1, you basically use this formula. Ax is a square variance x. Okay. So basically you take the constant out is square. So 1 over n square and variance of x1. This is the case. Now here is the key step is you need to know what is why a simple random sample, right? Is we have the covariance is being 0. So covariance of xi and xj is 0, or the independent. Okay. And if then they're independent, that means that this variance of the sum is just sum of the variance. Okay. And we learned that each variance is just sigma square. Right? So we have sigma square plus the n sigma square, so cancel out, right? So if n sigma square over n square, so what you left is sigma square over n. So this is the proof, and the main part is require the proof. Here is require simple random sample to go from here to this part. So the orange part is important, key. Other part are just simple algebra, right? Just basically, and we require this particular formula, right? So that is the formula is applied here, right? Other than that, everything is pretty straightforward, right? There's nothing new here. But why I want to cover these two functions is because it's so important in our analysis. And what is the key? What is the interpretation of this, right? Why we care about this? The important step is you can see is the variance of sample mean. Let me use the blue color. The variance sample mean is again proportional to sigma, but is inversely proportional to n. Okay, which means that if I have more and more n, okay, more and more n, you can see when n go to infinity, you will expect this guy goes to what? Goes to 0, right? Goes to very small, right? So that means that if I increase the sample size a lot, then the variance will exponentially drop, right? And it drop to 0, right? So that is one thing, right? That means that when you want your analysis later, we'll see to be more accurate, the easiest way to do just increase sample size, right? If you increase the sample size big enough, then we basically left no uncertainty there, right? We left very little uncertainty there, right? Just basically we can know for sure what's going on there. Okay, and in the other word is the dispersion of the sample mean will be reduced as n increase. Okay, so that is the key step here. And the other thing we want to often we use the note. I mean, that is something where often they mention in the textbook is called the cos-standard error of the mean. It's actually referred to the standard deviation of this guy. So standard deviation, take a square root, okay? Take a square root. This guy is cos-standard error of the mean, and later you will see why this is being used very often. But this is very important terminology, standard error. So you often see this happening. So basically, it means the standard deviation, okay? And particularly, we call standard deviation of the sample mean. It's a sample, the cos-standard error of the mean, okay? Now, with these two terminology, before we do that, let's see the example again, okay? So do you understand what the standard error or variance sample mean? So we have three numbers, 1, 2, 3, right? And population mean is just 2, right? And look at topic 1, how we calculate variance, right? You just take each number, right? And minus the mean and square, right? And there are 3 of them over 3, so it's 2/3, okay? So the first thing we want to show is if we have sample size of 1, okay? And the variance sample mean is again same as sigma, because this guy is sigma square over n, right? When n is 1, should be the same, okay? So from previous exercise, we already know the mean, the expectation of the sample mean is actually 2, right? So let's calculate this guy, right? 1 minus 2 square is 1, right? 2 minus 2 square is 0. 3 minus 2 square is 1, right? So, and 3 of them would appear 1/3 of time because simple random sample, right? And variance will be just this guy times this guy and sum up, right? So because this, right, it just is the expectation of this guy, right? Which is just summation of x minus e of x bar, right? Times p of x bar, right? So that's why you multiply plus multiply plus, okay? So end up the variance is just 2/3, which is exactly what we want, okay? So if just you collect one sample, okay? The mean is same as the population mean. The variance of this sample mean is just same as sigma square, okay? But anyway, this is not important, just to illustrate n is equal to 1 because you never have one sample anyway, okay? So look at the case we have 2, okay? And in that case, still we know when n is 2, we still have 2, right? We have shown that, right? Actually, it doesn't rely on how many sample you have, okay? And let's calculate the variance, right? When we have 1, okay, it's 1 minus 2 square, right? It's 1, right? And 1 up here, only 1/9. Remember the graph is we have 1, 1.5, 1.5, right? 2, 2, 2, 2.5, 2.5, 3, right? So 1 up here once. And 1.5 up here, 2 of 9, right? And let's calculate the difference. It's 1.5 minus 2 square. So it's 0.5 square is 0.25, right? So on and so forth, right? And this is 0.25 minus 2 square. This is 1 minus 2 square. So we have all this calculation here. And calculate the variance with this, multiply by this plus so on and so forth. Okay? So that's how we get this expression, right? And here we have this is exactly sigma square over n. N is 2. Okay? So here is, you can see immediately because we collect more sample, okay, the variance actually shrinks. Okay? The idea is the following. Okay, the intuition the following, right? Is you have the populations like this, okay? Maybe a lot of variance, okay? But the fact that if you just take 1 will be same as the original case, but you take 2 and calculate the average, it's likely to be more center than otherwise. right? Because the first time you're on the left, the next time is less likely on the left, right? I mean, it's very unlikely to be both times is very extreme. Okay, so it's very likely that it will be. It is more possible that everything is become more center, right? So it means the variance reduce, right? So that's why the variance getting smaller. Okay, so that is the second thing. Okay, I want to say. Okay, now go back to the idea we just said is the sigma square over n, right? Is the variance or sample mean, right? This guy, maybe just let me erase it. Right down here, right? What we have just found this guy. The sample mean is this, right? And as we have hinted, when this go to infinity, right? This guy should be go to 0, right? So it would immediately suggest that the following: this guy should be very close to mu, right? Because what we are saying is the following, right? Let's look at the graph again. Okay, so if this is x is the original population, right? We are saying that xn, okay, will have something similar, but the variance actually, I don't know what it looks like, but it's getting shrinks. When n get bigger and bigger, it will shrinks. I don't know how it shrinks, but at the end of the day, okay, it will shrink, but it will be something shrink as smaller and smaller and smaller, and getting smaller and more compressed. And at the end of the day, you compress to 0, right? And furthermore, you actually said it will actually goes to the sample mean, the population mean. Okay, so this is what the most important one of the most important theorem in statistics is what we call law of large number. It is essentially say, you can forget the notation, but what it means is if you have a sample mean, okay, it will be very, very close to the underlying population mean. Okay, when sample size get large, right? Because this is well expected because of the variance of this, right? Similar. I put a subscript n is because I want to signify this is depend on n. When this is actually go to 0, right? So back here you just say when n you're getting more and more, actually the function f or p just like shrinks, and actually this shrink to 0, which means that as I said here, right, the sample mean actually get closer to the population mean. Okay, and in terms of the definition is what we call the limit of the probability goes to 1. Okay, and I don't want to explain this expression, but essentially it's what I said. It's just like when it's so close, when n is very large, it's unlikely that the sample mean will be away from the true one. Okay, actually this forms the basis of what we do statistics, right? If this doesn't hold, then I have no hope of doing any data analysis, right? If we have very large sample, we can't figure out the truth, there's no point, right? That is idea of somewhat called deduction, right? We try to do induction, right? We try to collect evidence, right? We should be expecting at least, if we are able to collect as many evidence as we want, we uncover the truth. If that is not possible, then there's no point of doing anything, right? Because we never go to infinity anyway, but at least hypothetically, we go to, when you collect more and more sample, we should know what's going on. If this is not true, actually we don't need to study this class, right? Because that is the basis of learning, right? If there's not, if at the end of the day nothing to learn, right? If it doesn't go to 1, right? Is that clear? Why we have a law of large number is the basis of analysis. If that doesn't true, then basically all the bets are off because there's no way we can do anything. Okay. So this is rather technical, but this is important. And I hope that is clear. I convinced you this is right. At least you can see when you have more sample, the variance strengths, and it's strength to the sense that they would just collapse into one single point, something like that. Okay, the intuition. But the idea behind will be much more complicated. Okay. So if you learn calculus, this is epsilon limit idea. But anyway, the proof is rather complicated. I'm not going to prove anything on that. Okay. So the reason why we need central limit theorem is because, the law of large number is because it will give us an important theorem that we use through our class. So this is the main thing we will rely on for all the subsequent analysis, okay, which is known as central theorem, which said if we have large enough sample, again a limit, right, a limit theorem, it means that the sample mean, okay, will be a bell curve. Okay, sample mean will be a bell curve. Okay, and so this is saying, right, the x bar, okay, x, no matter what it looks like, okay, I don't know what it looks like, but x bar, when n get very big, this n bar must be a bell curve. Okay. More importantly, the bell curve, I mean, actually, by simple random sample, this is already mu, right? And this is sigma squared. Do note that these two do not rely on central limit theorem. Okay. We know that already, right? Because the expected x bar, okay, is mu, right? Variance of x bar is sigma squared over n. Okay. So that's nothing new here, but we say the bell curve is important. Okay. The key step in this one, the central limit theorem, is saying that the sample mean, okay, is following a bell curve. It's important. Okay. And the actual statement actually will be like this one will be sample mean minus mu over this, as we call the sample standard error, will be normal 0, 1. Okay. And if you study why I have two different forms here, and because of the fact that the actual proof is proving this guy. Okay. Okay. This is the one this is actual central limit theorem, but essentially this is mean this, all right? But the proof is we actually proving this guy, not proving the above. Actually, the central limit theorem is actually the green guy, but we can imply the loosely speaking, we can imply the above. Okay. And probably you would ask, this is the bell curve only appear when n go to infinity. Okay. So what does it relevant in our practice? The fact that, I mean, if the rule of thumb will be when sample size n is at least 35, okay, actually we can use central limit theorem, which is usually the case to satisfy in all the business application, right? 35 should not be an issue. You have 35 customer. If you don't have 35, probably you don't need to do statistics, right? I mean, unless you can, you should be able to collect 35 sample, okay, and shouldn't be an issue. Is that clear what we're doing? Okay. So it's very powerful. Okay. Let me repeat this, how powerful it is. Because of we do not care what the population looks like. It can be normal. It can be normal. Of course, normal get normal, but it can be exponential. Okay. Can be any shape you can imagine, regardless of what you like. It doesn't really matter. It can be uniform, can be anything. Okay. The key part is I don't need to care what it is. Okay. It tells me the central limit theorem allows me to do a bell curve if the n goes large enough. So this is a like magic. Okay, it's really a magic because It doesn't rely on, we don't really need any assumption. As long as we have simple random sample, we do sampling in a correct manner, we carefully do sampling, the sample mean will follow a normal, which is a magic, right? I mean, I don't know how you like, but if you really think about carefully, just like something, I mean, not it's easy to realize how important they are because you learn the math, right? It can be anything, right? But at the end of the day, the sample mean is indeed the bell. So I can't emphasize anymore, but this is essentially the main tools we will use for the rest of our course. We will rely on this particular formula to do many analysis we need. Okay. Is that okay? So now let me end this first half of our section with this example after the break. Okay. So this is rather simple. Okay. It's applying central limit theorem. Okay. So here we have the population mean 5 and variance 64. Okay. So this mu is 5, variance 64. That means that the sigma is 6. No, it's 8, sorry. 8 times 6 is 64, right? So do look that I didn't mention about anything about the population. It can be exponential, can be uniform, can be any weird shape. It doesn't really matter. We didn't need to know. Okay. As long as we have a random sample, okay, of size 100, okay, and we can calculate this statement, no more than 4. Okay, we can calculate this. It's rather surprising, right? Because you don't need to know what the population is. Okay. So as we learned, the central limit theorem said the following, right? This guy minus the mu over sigma over root n is actually z. Okay. This is actually the central limit theorem tells you is you minus the mean over standard error is a standard normal. Okay. So that's why you subtract 5 on the both side equation, right? So let me show you how to do this, right? 4. And you subtract mean from both side equations, right? You learn from the inequality actually is valid, right? You subtract 2 things from the both sides is valid. Okay. The second thing is I divide, let me use another color, divide sigma square over root n, which is sigma square is 8, okay, over root 100. This is a positive number, okay. You divide positive number on both sides inequality, that will preserve the inequality, right? So because you're dividing positive number, okay, so that ends up in this guy, right? Because this is negative 1 over 8 over 10, right? It's 5 over 4, right? So it's 1.25. Okay. So so then let's calculate this guy. I mean, it's good, I think, now to show you how we do Excel, right? Because how to figure out this number, right? Since we have done Excel, so let's quickly. Oh, I don't know why. Activation. Why? Okay, they don't allow me to. Why? Let's see. Okay, I cannot do it for some. Okay, cannot do it. Then let's look at the Z table. Okay, too bad. Maybe I can do Google Sheet. Cannot. Very annoying. So let's look at the C table. So we have the Z table. we have a negative 1.25. So we look at 1.2 here. I don't know, maybe. Okay, that's good. So negative 1.2 is here. Okay, 1.2 is here. 1.25 is over there. So 1.25. Okay, I don't know whether you can see clearly. 1.25 is this guy. 0, 1, 2, 3, 4, 5 is this guy. 0.1565. Okay. So I don't know why the Excel doesn't work in this computer. Maybe they have to get it done. But you can. But I write down the formula for the Excel. If you try this at home, if you want, it's just the norm S this, right? Negative 1.25 true. Okay, will be the formula. Okay. Y dot S is the standard normal. Y true because look at the big F, right? Because for the continuous, always look for true. Okay. So that would be the answer. So that is the way we do it. Okay. So although this example look artificial, but later you will see we often use this guy, very often, when we do hypothesis testing or estimation. Okay. So let's have a break of 10 minutes. We'll resume at 10 minutes later. Okay. Okay, so let's resume. I guess it may be fruitful to talk once more about what we have covered, because some of you still not fully understand. So very quickly. So the thing we want to study is sample mean, because later you will see we care about the sample mean because sample mean can tell us a lot of things. So that's why we study some property of those, right? Sample mean just average of these observations. And do note that this is a random variable. And first key thing is saying the sample mean, expectation of sample mean is actually the population mean, right? Do recall what do you mean by that? Is mean we potentially can have many possible sample, okay? And this each sample you have different sample mean, okay? And it can be different from mu, but on average, its hitting is equal to mu. Just look at this example, right? Remember the sample population mean is 2, right? But you can have 1.5, 2.5, 2.5, 1, and 3. But on average, it's hitting 2, right? And you can easily imagine we can increase the number of sample, right? In that case, you could imagine that you can have a very complex table, but at the end, all this entry will be very close to 2, okay? That means the central limit theorem is when n go to very big, okay? You can imagine that this shrinks, right? This range shrinks, and it's very unlikely you have 1 and 3, and most likely you have a lot of 2s and somewhere near 2s, okay? That's law of large number, okay? And the central limit theorem further tells you that how does this table looks like? And at the end looks like a bell. That's what it means. Okay, this one doesn't look like a bell that much, but you can imagine if you increase the sample size, that thing will eventually look like a bell. Okay, this one doesn't look like a bell, right? But you can easily, but you can imagine that if I have much larger sample size, the value must be 1 to 3, but at the end you will, right? Here is like, looks like this, right? It's 2 is like this, right? 2, 1.5, 2.5, 3, and 1, okay? And if you increase the sample size, at the end, it looks like a bell like this, okay? Look like a bell, right? And you keep increasing, it will be even look like this one, right? And at the end of the day, maybe look like this, right? And smaller and smaller and smaller become a very sharp, right? And become so sharp that become law of large number, right? And the shape every time you see a bell is actually the central limit theorem, right? Every time it looks like a bell. Okay, I hope this graphical explanation will give you a better idea what we are doing. And you may ask, okay, it's a bell, so what? Okay, and the next topic will try to use this bell idea to help us to do prediction, okay, to estimation, and we do hypothesis testing. But that will be next thing. So just to remind you one thing, probably you have to carry over to next class is the sample mean, okay? When the sample size get large, then you have bell curve. That is something you need to remember. Okay, the key step, because this is what we call central limit theorem. Okay, and do note that this, regardless of what the underlying distribution is, right? Here I have uniform 1, 2, 3. Okay, you can change to any distribution. Central limit theorem or law of large number applies. Okay, it holds regardless of what we have saying. Okay, I hope that is clear. Okay. Now, one thing that we probably want to look at is in business application is we have looked at binary data. Okay, is we try to ask whether you like the product or not, right? Whether you you have a pet or not have a pet, right? So this is yes or no, success or failure, right? And this is very important. Okay, so basically what we are saying is we restrict to a special case where we have a population, okay, with a bunch of 0 and 1. Okay, 1 maybe mean they like, say, suppose they ask, do you like cats or do you like dogs? Then yes is 1, no is 0, right? And the proportion of people of 1 over total number of people is called pi. Okay, so that is what we call the pi is called population proportion. Okay, it's just total number of people who is 1 and total number of people in the population. Okay, so that is the what do you mean by pi? Okay, it's the proportion of the people who got 1. Okay, so that is what it means. Okay, and if we do simple random sample in this framework, it is indeed each observation actually is a Benoni, right? Because you draw one guy there, probably that is 1 is actually pi. Okay, so the mean, okay, of this drawn will have pi, and variance will be pi times 1 minus pi. That is coming from the Benoni, if you recall. Is that okay? Because Benoni is either success or failure, right? And Benoni, the mean is pi and the variance pi times 1 minus pi. Is that okay? Is that okay for this one? Okay. If that's okay, so let's define the sample mean in this framework. Okay, sample mean in this framework is actually sample proportion. Okay, because it's 0 and 1. Okay, why it's called sample proportion, right? Suppose you have taken a sample size of 10. Okay, and actually there are 3 of them. Say, suppose you have 1, 0, 0, 1, 1, right? 0, 0, 0, 0, 0, 0, right? And there are 10 samples, right? And how many of them say 1, 3, right? So the sample mean is just 3 over 10, right? Because you add them up divided by n, right? So actually this sample mean is actually proportion, right? It's proportion of people who got 1, okay? And we denote this as P. Okay, is that clear notation? Okay. So that's why it got sample. It's basically sample proportion. It's just actually the sample average, but you restrict to the number of 0 and 1. Okay. So just proportion, just saying that suppose you care about the data is number of people who like cats. Okay. And then you got 3 people who like cats and 7 people don't like, right? So the P is just 0.3, right? Because 3 people like, right? 3 over 10. Okay. But this is the same as adding all up divided by n, right? The sample proportion is just the sample mean, no difference. Is that okay? So why we want to talk about this is because the following. the thing we learn, we apply, right? Because the expectation of sample proportion is the population proportion. What does that mean? It means the following, okay? Suppose your population, okay, pi of them is 1 and 1 minus pi is 0, right? Say maybe pi, say suppose pi is say 0.7 or 0.3, maybe 0.3, right? That means that maybe you have hundreds of people there, 30 of people like cat, right? And P, okay, you basically say suppose you have 10 people, right? And maybe once you draw a sample, you may have 2 people who like the cat, 8 don't like, maybe 3 and 7, and 1 and 9, and many combinations, okay? When you draw each sample, okay? And each sample you can calculate the proportion, okay? Sample proportion, and average of this sample proportion is indeed will give you pi again, okay? The idea is exactly same as the expected, remember this, expected X bar is mu, okay? But now X bar in our context is a P and mu is just pi, okay? So that's why we have here. So there's nothing new here, except that the data becomes 0 or 1, that is a thing. Is that clear? Is that okay? Now, here is a little bit trickier, but nothing new here is sigma square. In our case, is pi times 1 minus pi. Okay, so that's why the interesting part is the variance. Okay, is pi minus 1 power n, right? But the mu of p is also pi. Okay, so one interesting part is look at the proportional or binary data is the sample mean and the sample variance are related, right? Because remember, if we have X bar, it's just mu, and this guy is sigma square over n, and they are unrelated, okay? So they are unrelated. But in the current context, the variance are related by pi, okay? It's pi over pi times 1 minus pi over n, okay? So this is actually one of the very important point that you have to remember, because this is, we'll use it again. This is a very important step, okay? And the reason is, okay? The reason is being the difference is we can estimate this guy, right? By using the sample, later you see, by using the sample proportion, right? And by estimating sample proportion, we also estimate this directly, okay? So this make this binary problem much easier. But for the general sample mean, they are different. So you have to come up with a way of estimating mu and estimating with sigma square, okay, to do anything, okay? You need to know sigma square, because sigma square we don't know, right? So that actually related to some of you ask me why we learn S square when the topic 1, right? With sample variance. Later we will see the sample variance to estimate sigma, but that will be left for the next topic, okay? But that is the main key difference between binary data is for binary data, you don't need to separately estimate the variance, sigma, because sigma is actually given by pi times 1 minus pi. So that actually gives binary data much easier to handle, right? Because you don't need to know sigma square, right? Because once you know the pi, you have a good estimate on pi, you have good estimate on the standard error, okay? Standard error like this, it's just a square root, okay? There's nothing new here. Is that okay? Okay. Now, so that would be the same. The central limit theorem applies, okay? Because binary data is also have a central limit theorem applied, right? That means that this guy, right, the sample proportion follow a bell curve. Okay. Do look that this is also a interesting because I don't care how my data looks like, right? I don't really need to care about the pi, right? I don't care if as long as I have 0, 1 data, okay? I don't really care about how many ones are out of zeros, right? I don't care about pi. At the end of the day, if you look at the sample mean, it's always normal. It's always bell curve, right? Whenever I ask a question, it's about binary, okay? I don't really need to care about whether there are many people like cat or very few people like cat. I don't really need to care. Then I always have a bell curve, okay? And there is some remark here is, although I say it's independent of pi, but for this to be good approximation, you need to make sure that n pi or n times 1 pi at least 5, okay? Which means that if your pi is very, very small, this approximation fails, right? So if you are looking at the population that only very few people like cats or so many people like cats, then it wouldn't work. Okay, if pi is so big or so small, the n pi is not at least 5, then it's a problem. But usually it's not an issue because n pi plus this should not be, and practice that should not be an issue unless looking at very, very rare stuff. But in general, for business application, that should not be an issue because if pi is so big, then you pretty much know what's going on. Or pi is so small, then you probably don't need to do anything. So that would be the thing. Okay, to basically just repeat what we have said, but just because binary data, we don't have a sigma there, we just have pi. Okay, so that is the main difference here. So I just want to highlight one thing, but without going into detail, is what we call normal approximation. Okay, which sets, I often said the binomial. Okay, if x follow a binomial, okay, and with np and n minus p are at least 5, okay, actually we can do approximation. Okay, this actually follow a normal distribution. Okay, so that is actually you can say come from the central limit theorem. Okay, we have just seen, and it's very useful when the days we don't have computer, right? Only useful when you don't have computer. In the old days, that is a very useful technique. Okay, and now I don't think actually we need anything this more because we can calculate exact probability, right? Excel tells you exact one, but this in some sense explain why always the normal is because of binomial. Okay, actually will go to normal or can be close to normal when these are close to 5. Okay, so that is one important implication of central limit theorem, right? It's like binomial actually go to normal, and indeed that actually explains why we also see t goes to normal, f go to normal, exponential go to normal. Every graph actually where go to normal. Okay, so that would be one thing I want to add. But it's technical, so you don't need to worry about this part. But just try to justify the early statement we said is everything looks like normal, right? So here actually we have some reason why this is true. So this is example. Let me quickly go over it, but it's not very important. So it's technical part. So I just do that. Okay. So this is the example, okay, of a normal approximation. The idea is following. So not our problem. X is a binomial with n 100 p.6. So what is X is less than 55? So that's the question. Okay. And we can use the idea that this guy, okay, is actually a normal with n p, okay, n p 1 minus p, okay. So that would be the normal approximation, okay. So that's why you take this subtract from is np, right? This is np 1 minus p here, right? So then you can do the rest of the calculation. Okay. So because when it's normal, okay, when it's a binomial, this is a good approximation. Okay. And again, it's not very important, so I'm not going to go step by step, but this is what we have. Okay. But it's not very important these days because of now we have a computer. Okay. Is that okay? I think it's interference from other room. Nothing you can do right now. Okay. So I just go quickly over this one. Okay. So now I guess it's good to talk about this now because this explains why we have S squared. Okay. Why someone asked me why we learn in topic 1 why we have S squared. Okay. The thing is we just learned central limit theorem said the following, right? If we have large enough sample where n is bigger than 35, which is a good approximation, the sample mean, okay, minus the mu over sigma over n is normal. Okay. The problem is, the problem is the following, okay, is this guy. What's sigma? We don't know. No idea without sigma. Because sigma is independent of the mu, right? So sigma can be anything. Okay. Even though you have the sample mean, okay. When you have sample mean, you have a good knowledge of mu might be, right? But sigma is very difficult to have a good knowledge. All right. And how can we work about this? Okay. And turn out to be, we'll talk about next class, is to estimate sigma 1 or sigma square. One of the good things is we will estimate through S, which is divided by n minus 1. Okay. We will try to show you that why n over 1 would be good. Okay. And when we replace it by S, okay. So this is what we want to know. Okay. This is what we want to know. What's this guy? Okay. What is this guy? Can we know anything about this guy? Okay. And in general, we don't know the answer. Okay. We generally don't know the answer. Okay. How do we proceed? Okay. Is assume, okay, which is a strong assumption here. Okay. To proceed, we need a strong assumption, which we call normality assumption, which assume with a bell curve at the beginning. Okay. Here is very strong. Okay. Before we don't rely on the bell curve, but now we have to say we are drawing from a bell. Okay. X is also a bell. Okay. And if we are the underlying population is a bell, then we have what we want. Okay. Probably you would ask, what happens is not a bell? That is beyond our class. Okay. We focus on the case, the underlying population is a bell. Okay. If that's the case, we can say the following. If it's a bell, okay, underlying is a bell, okay. The first thing is we can have a much stronger result than central limit theorem, right? Central limit theorem said n bigger than 35, this thing holds, right? But if we under normality, okay, this is true for any n, okay? Even if n equal to 1, that's also true. Because you start from bell, okay? You start from bell, this sample mean also a bell, right? But it's of course much narrower because you have a smaller variance, okay? You can see the ray I draw is shrinks, okay? So here we have to assume the beginning we have a start with a bell, and then at the end we have a bell but a narrower bell, right? Look, this is the mu, okay? And this is sigma square, and this is become sigma square over n. N here, this mu, okay? So this is the graph it looks like, okay? So is that clear what we are having? Okay, so we need to assume we're drawing from bell, okay? And once you draw from bell, then actually the sample mean is also bell, but it's narrower bell, okay? And this actually can help us to do the following analysis, okay? That is, again, this is the key, or I would say the key equation that we use in our class. Central limit theorem is the theorem, okay? But this is the thing we use basically for our course, is under the normality, okay? I mean the sample mean, okay? The following is a t distribution. So that means this guy is t with degree n minus 1, okay? So remember, t is actually a standard normal over a chi-square n over n, right? Take a square root, okay, will be t of n. Okay. But we are not going to prove it. So in some sense, what it's saying is the following. Okay, let me draw a diagram to show you what were we doing. Okay, so now because of we don't know sigma, so let's start the following. We start with x, okay, it's a bell. So mu and sigma square is with the starting point is here. Now we are doing some sample, okay? What we're going to do is just try to draw an observation here, right? Average those, right? And you draw to the other side, right? Which is x1 up to xn, the other n, right? Just you randomly draw n from this bell, okay? Average those, okay? Will again give you a bell, okay? And the bell will be much narrower because the variance is just over n, right? Because the more sample you had is more narrow, right? Is that okay? It's still a bell. Okay? Is that okay? Now, the problem of this expression is this guy rely on sigma square. We don't know. Okay? Because we don't know sigma square. How can we proceed? Okay? To proceed, we just consider the following. Okay? We consider let me go one more step. That means that x n minus mu over sigma over root n is just 0, 1. Okay, this is standardized normal, right? That's that. Okay, this is a standard normal. Okay, this is the standard bell curve. Okay, standard bell, right? It's a bell where mean 0, variance 1. Okay, so this is what we know so far. Okay, so the question is being, okay, we don't know this sigma, right? How can we proceed? How can we start? Okay. The idea is being proved by what we call the guy called student. Okay. Is this over S over root N. Okay. So we don't know sigma, but we replace by S. Okay. S is something we can calculate, which is S squared come from x1 minus x bar square over n minus 1, take a square, okay, xn minus x bar, okay. So that would be the calculation, right? And this guy is actually we call a looks like bell. It's a T bell instead of bell, T bell. Bell is this T is n minus 1. Okay. So actually we look at the table, but don't worry, this will be it's like a bell, but it's very close to bell. Okay. As I mentioned, if n is like more than 200, it's almost exactly the bell. Okay. But it's below 200, it's like a bell. The bell look like this. You could not if the bell is like this, look like this. The bell is look like this. If you look at the red one, look like this. But when we say the sample size is not that large, you need to adjust a little bit. Okay. So basically, what it said is we don't know sigma, so we have to use the sample variance. Look at the sample variance n minus 1, and in that case, if we replace it's okay. Everything looks the same, but we cannot use the original bell. You can use the little bit different bell. Is that clear what we are saying? Okay. So it will become more clear why we learn this in the next class, but this is what we're. Oh, I'll go back to this one. I think someone to take picture, and I think I want to also take picture as well because I think this is good. I like this graph. So that's exactly what you mean. Okay. Do remember that we start from a bell here. Okay. We start from a bell here. Okay. And of course, you would ask, where do we look? Do we need central limit theorem here? Yes, we do, because the proof of this guy, why this guy end up like this, there's something there. But anyway, I don't think we need to talk about those. Okay. So I guess this is the last example. Okay. We have is the following. Okay. So the question is, we start with a normal distribution. So this is important. Okay. We need that for our analysis to work. Okay. With mu5. Okay. So basically what it said is X, okay, has a normal distribution with mean 5. Okay. But I don't know the sigma square yet. Okay. We don't know this guy. Okay. And the sample size is 100. So n is 100. Okay. So we also know the second thing, the sample variance is 8. Okay. So S squared is 8. Okay. So do note that the sample variance is you got the sample, you calculate sample mean, and you subtract every observation from the sample mean square and over n minus 1. All right. So just to remind you what is it is, you have x1 minus, I don't know the sample mean here. Okay. And you do because you're 100. Okay. And you have x bar and over 99. That is the sample variance. Okay. The question is being asked is, okay, if you know the sample mean is 5, okay, and what you want to see is what's the probability no more than 4.5. Okay. So later I'll explain why we look at this statement. Okay. But let's calculate and then I'll explain why we look at this statement. Okay. And the first thing we know is this guy is following T. Okay. This is what we just said, the previous page, right? You just minus the mu, right? This minus the mu over S over root N is T N minus 1, okay? Is T99, okay? So that's why you subtract 5 on both sides, right? 5 is the mu, right? This is S square over root N, right? So this guy less than 4.5. So the first thing is minus 5 on the both sides. Maybe I just do step by step because I think it's good to know what we're doing. Minus 5, okay? And then you would over, this is same as square root of S square over root N, right? So same as square root of 8 over 100. Okay, sorry. Right? So both sides square root of 8 over 100. Okay? And this guy is negative 1.76. Okay? So, and this one, I didn't tell you how to do it in Excel, but that is the same as the normal. It just T dot this. Okay, in Excel, T, because T dot this. It's just negative 1.798. And because of 99, you enter 99. And then you put true. And then you're done. Okay. And I'm not sure Excel would work. Probably not. Oh, it works. Nice. Surprising. What happened? Some magic happened. So you would do T this, okay? Negative 1.769, 99. Remember, a continuous always true, okay? So this is the number. So this is the number, 0.004. So that is very small, but that is what we expect, okay? So probably the first thing is you ask why we care about this thing, why you want to calculate the sample means less than certain number, okay? Actually, this is what highlight 2 topics after hypothesis testing, okay? And here is the following. Maybe someone claim, that's what we will do later, but that's what the idea is. Someone tried to claim their food has 5 grams of active ingredient, okay? Maybe ingredient is orange juice or whatever, right? So maybe a orange juice has 5 grams of very useful thing, right? And you want to see is actually this is right? And if this is, I mean, but of course, you know, by production, right? There will be, although they say it's 5 grams of this useful substance, right? And you assume normal, right? It can be more than 5, less than 5, right? Depends on the production process, right? As long as on average is 5, they're not cheating, right? Because the 5 grams can be less or more, right? The idea here is, okay, now you got the data, you got a sample, okay, you only got 4.5, okay? And you ask the question, is the firm is cheating, okay? The idea is like this, assume they're right, okay? The probability that end up with less than or 4.5 is very small. It's like 4%, right? So it means that what the firm claiming is not quite right? But let me repeat what we are doing here. Actually, we'll do it more detail next week or onward. It's called hypothesis testing. Hypothesis testing. Okay, this is the claim. How you get the mu? Mu is a claim made by a manufacturer. Okay, they claim there are 5 grams of this inside that, right? Okay, and you figure out that, okay, the sample mean you get is 4.5. Okay, and then you would like to jump up to claim the firm is cheating. How do you do that? Is to calculate the probability that is even worse than it happened, okay, which is very small. Okay, that means that it is very unlikely that the firm is telling the truth. Okay, so it's very small. It's 4%. Usually the threshold is 5%. Okay, if if you're less than 5%, okay, then something is very unlikely to happen. Okay, then you would not say yes. Okay, so the repeated idea is the following, right? Because 4.5 is much less than 5. Okay, and how small? How do we measure? The measurement is look at the area. Look at this small area, the tail area. If the tail area is very small, then we will say the distance is large enough to say this is not true. Okay, because the bigger the distance, right, the smaller this area. So instead of looking at the distance, we look at the area because that reflects the probability, right? But of course, we will talk about this next week. But that's the main thing. Okay, I guess we can end here because the rest are rest of the just technical slides which we don't really need. So basically, we finish this. Okay, so I will see you on Thursday.